Imagine a world where things can exist in two places at once. Welcome to the strange world of quantum physics, a realm where the ordinary rules of reality as we know them take a backseat and a whole new level of extraordinary takes over. Quantum physics, also known as quantum mechanics, is a branch of physics that deals with phenomena on a very small scale, such as molecules, atoms, and subatomic particles like electrons and photons. But what sets quantum physics apart from classical physics, the kind we're more familiar with, is the sheer unpredictability and peculiarity of it all. In the quantum world, particles can exist in multiple states at once, a phenomenon known as superposition. Picture this as a coin spinning in the air. It's neither heads nor tails, but both at the same time until it lands. Bizarre, isn't it? Then there's the concept of wave-particle duality. Here, particles like electrons and photons behave as both particles and waves. Imagine being at two places at the same time or being in a state of doing two things at once. That's what these particles do. And let's not forget the uncertainty principle, which states that you cannot simultaneously know the exact position and momentum of a particle. It's like trying to catch a slippery eel in the dark. You might have a vague idea of where it is or how fast it's moving, but never both at the same time. But hold on to your hats, because we're only scratching the surface of the quantum realm. Now, let's delve deeper into this curious world, starting with a paradox that baffles even the greatest minds. Schrödinger's cat. Ever heard of a cat that's both alive and dead at the same time? Welcome to the Schrödinger's cat thought experiment. Now, imagine a cat in a sealed box. With it, a tiny amount of radioactive substance, a Geiger counter, a vial of poison, and a hammer. The radioactive substance has a 50-50 chance of decaying within an hour. If it decays, it triggers the Geiger counter, which then releases the hammer to smash the vial, releasing the poison and, unfortunately, killing the cat. In classical physics, the cat's fate is uncertain until we open the box. It's either dead or alive based on whether the atom decayed or not. But here's where things get weird. According to quantum mechanics, until we check, the cat is in a superposition of states. It's both dead and alive. This thought experiment was proposed by physicist Erwin Schrödinger in 1935. It's not about animal cruelty, but rather, it's a critique of what's called the Copenhagen interpretation of quantum mechanics. This interpretation suggests that a quantum particle exists in multiple states at once until observed or measured, at which point it collapses into a single state. In Schrödinger's imagined experiment, the cat's life or death is tied to the state of a quantum system, the atom. If the atom has decayed, the cat is dead. If it hasn't, the cat is alive. But since the atom is in a superposition of states, until it's observed, the cat, by extension, should also be in a superposition of states. Sounds bizarre, right? The point Schrödinger was making is that it's absurd to apply quantum mechanics to everyday objects like cats. This paradox has sparked many debates about the interpretation of quantum mechanics and the nature of reality itself. As bizarre as it sounds, this thought experiment is a cornerstone in understanding quantum superposition. Imagine being in all places at once until someone observes you. Welcome to the world of quantum superposition. This peculiar concept is one of the cornerstones of quantum mechanics, where a particle can exist in multiple states simultaneously. Sounds strange, right? But hold on, it gets more intriguing. This idea of superposition is closely tied to the famous thought experiment of Schrödinger's cat. Here's a quick refresher. Schrödinger proposed a scenario with a cat in a locked box with a tiny bit of radioactive substance. According to quantum laws, the radioactive atom could either decay or not decay, and thus the cat inside the box could be both alive and dead at the same time. You heard it right, both alive and dead, until someone opens the box and observes the cat. This is quantum superposition in action. So, how does this work? It's all about probabilities. In the quantum world, particles don't have definite properties until they're measured. Instead, they exist in a haze of probabilities. For instance, an electron in an atom doesn't orbit the nucleus in the way planets orbit the sun. Rather, it exists in a cloud of possible locations, and we can only calculate the probability of finding the electron in a particular place at a particular time. But here's the catch. As soon as we measure the electron's position, it chooses one of the possible options, and the superposition collapses. This is known as the observer effect, and it's one of the most mind-boggling aspects of quantum physics. It suggests that the act of observation is what brings particles into a definite state of existence. So coming back to our feline friend, as long as the box remains closed, the cat is both alive and dead. But as soon as we open the box and observe, the superposition collapses and the cat must be either alive or dead. But how does observation affect this superposition? Let's find out. Your mere observation can determine the fate of a quantum system. Intriguing, isn't it? Welcome to the fascinating world of quantum mechanics, where the simple act of looking can change everything. In the quantum realm, particles exist in a state of superposition, meaning they can be in multiple states simultaneously. But here's the twist. When we measure these particles, we only ever see them in one state. Why is that? This is what we call the observer effect. It's the idea that by merely observing a system, we influence it. In the quantum world, this influence is so profound that it can actually collapse the superposition. This means that the multiple potential states of a particle reduce to a single state the moment we measure it. Imagine you have a coin spinning in the air. While it's in motion, it's essentially both heads and tails at the same time. This is the superposition. But the moment the coin lands and we look at it, it's either heads or tails, not both. This is the observer effect in action. But how does this work? Well, that's one of the great mysteries of quantum mechanics. Some scientists believe that the act of measurement physically changes the system. Others suggest that the system was always in a definite state. We just didn't know it until we looked. So what's the role of the observer? Some interpretations of quantum mechanics attribute a special role to the observer. In these views, it's the conscious act of observation that causes the collapse of the superposition. But this idea is controversial and not universally accepted. Regardless of the interpretation, the observer effect highlights the strange and counterintuitive nature of the quantum world. It challenges our everyday understanding of reality and forces us to question what it means to observe and to know. But how does the quantum world interpret these observations? Let's explore. Does observation collapse the quantum world into one reality, or does it create many? Let's dive into the interpretations. In the heart of quantum mechanics, two interpretations have taken center stage: the Copenhagen interpretation and the many worlds interpretation. Each offers a unique perspective on how we should understand the seemingly paradoxical phenomena presented by quantum mechanics, such as our befuddled friend, Schrödinger's cat. The Copenhagen interpretation, named after the city where it was first formulated, proposes that the act of observation collapses a quantum system into one definite state. Before you peek into Schrödinger's box, the cat is both alive and dead, suspended in a superposition of states. But the moment you look, the superposition collapses, and the cat must be either alive or dead. The observer, in essence, brings about the cat's fate. On the other hand, the many worlds interpretation, as the name suggests, proposes an infinite number of parallel universes. Each universe represents a different possible outcome for every quantum event. So, when you open Schrödinger's box, you don't force the universe to choose between a live cat or a dead one. Instead, the universe splits into two, one where the cat survives and another where it doesn't. You, the observer, merely find yourself in one of these parallel realities. Both interpretations provide intriguing solutions to the quantum conundrums. The Copenhagen interpretation leans into the inherent uncertainty of quantum mechanics, while the many worlds interpretation promises a deterministic but infinitely complex multiverse. So, which interpretation is correct? Well, that's still a matter of heated debate among physicists. The truth is, quantum mechanics is so fundamentally different from our everyday experiences that our intuition struggles to keep up. But it's this very strangeness that makes exploring the quantum world so captivating. Quantum entanglement adds another layer of complexity to these interpretations. Let's unravel it. Welcome to a world where particles, no matter how far apart, are mysteriously connected. This is the mind-bending realm of quantum entanglement, a phenomenon that Albert Einstein once described as spooky action at a distance. In our everyday life, we're used to the idea of cause and effect operating under certain spatial boundaries. If I push a swing in a park, it moves, but it certainly doesn't affect another swing in a park miles away. Yet, in the quantum realm, things don't quite work that way. Quantum entanglement is a phenomenon where pairs or groups of particles interact in ways such that the quantum state of each particle cannot be described independently of the others, even when the particles are separated by a large distance. This means that measuring the state of one particle instantly determines the state of the other, no matter the distance between them. Imagine you have a pair of gloves, one left-handed and one right-handed. You put each in a box and send them to opposite ends of the universe. Now, if you open one box and find a right-handed glove, you instantly know that the other box, no matter how far away, contains a left-handed glove. That's a simple analogy for quantum entanglement. The implications of quantum entanglement are vast and still not fully understood. It challenges our understanding of the very nature of reality. It suggests that the universe is deeply interconnected in ways we're only beginning to comprehend. It's also worth noting that quantum entanglement has practical applications. It's a key principle behind quantum computing and quantum cryptography, technologies that could revolutionize the way we process information and secure our communications. So, we find ourselves in a universe that is much stranger and more interconnected than we could have ever imagined. Quantum entanglement, with its spooky correlations, is a testament to the beautifully complex tapestry of reality. Quantum decoherence attempts to reconcile these bizarre phenomena with our classical observations. Let's see how. Why don't we observe superpositions in our everyday life? Let's find out with quantum decoherence. As our journey through the quantum realm continues, we now find ourselves grappling with a rather perplexing question. Quantum superposition allows particles to exist in multiple states simultaneously, but why don't we witness this phenomenon in our day-to-day life? The answer lies in a concept known as quantum decoherence. In the quantum world, particles can exist in a state of superposition, where they're in multiple states at once. However, when we observe these particles, we see them in only one state. This transition from quantum to classical is where quantum decoherence steps in. Decoherence is the process that transforms the quantum world's strange behavior into the predictable reality we're familiar with. It's a bit like a translator, converting the language of quantum mechanics into classical physics that we can understand. When a quantum system interacts with its environment, the superposition of states starts to disappear or decohere. This is because the quantum system is no longer isolated. It's constantly being measured by its surroundings, which causes the superposition to collapse into a single state. In a way, quantum decoherence is the bridge between the microscopic world, governed by quantum mechanics, and our macroscopic reality, dictated by classical physics. It's this process that prevents us from seeing cats that are both alive and dead, or particles in two places at once. Interestingly, some theories suggest that the quantum superposition doesn't actually disappear, but simply becomes unobservable to us. According to these theories, every possible outcome of a quantum event exists in its own separate universe, as part of a multiverse. But that's a topic for another time. Decoherence doesn't solve all the mysteries of quantum mechanics, but it does offer a plausible explanation for why the weirdness of the quantum world is hidden from our everyday experiences. The study of quantum decoherence continues to be a vibrant field of research, with potential applications in quantum computing and other emerging technologies. Now that we've unraveled the mysteries of quantum physics, let's look at its real-world applications. Quantum physics isn't just theoretical, it's shaping our world in surprising ways. Real-world experiments, such as the famous double-slit experiment, have tested and confirmed the principles of quantum mechanics, pushing the boundaries of what we once thought possible. These experiments have paved the way for emerging technologies that leverage quantum phenomena. Quantum computing, for instance, harnesses the power of superposition and entanglement to process information at speeds unimaginable with classical computers. Meanwhile, quantum cryptography uses the principles of quantum mechanics to create unbreakable codes, promising a future with secure communication channels. And let's not forget about quantum teleportation, a concept straight out of science fiction, is now a reality in labs around the world. Each of these examples highlights how quantum physics is not just about understanding the universe, but also about leveraging its peculiarities for practical applications. Quantum physics, with all its paradoxes and complexities, continues to challenge our understanding of reality. We've journeyed through the fascinating world of quantum physics, from Schrödinger's cat to quantum entanglement. We've peeked into the peculiarities of quantum superposition, where particles can exist in multiple states simultaneously, and delved into the role of the observer in collapsing this superposition. We've also navigated the depths of quantum decoherence and its role in reconciling the quantum world with classical observations. We've explored the Copenhagen and many worlds interpretations, each offering a unique perspective on quantum mechanics and its paradoxes. We've highlighted the intriguing phenomenon of quantum entanglement and how it adds complexity to the nature of quantum reality. Finally, we've touched upon real-world applications and experiments that test these principles and the challenges that remain in this field. As we continue to explore the quantum world, who knows what other mysteries we'll uncover? Stay curious and keep exploring.